Chapter number 2. Kinematics, part 1. Displacement, shortest distance between the final position and initial position, is called displacement. It is a vector quantity. It may be positive, negative, or zero. It is numerically equal to final position minus initial position. We have the example of a rectangle. We have two paths, but the displacement will be AB. Now we have the circle. We start from A and again reaches point A. So the displacement is zero because final position and initial position coincide with each other. Now we have a zigzag line. Here we start from A, it reaches point B. So the displacement is AB. Now we have another figure of a curve. Here OA is the initial position vector, OB is the final position vector, S is the displacement vector, and that is why S is equal to OB minus OA, that is equal to AB. Now we will understand distance. Total length of the actual path traveled by a body is called distance. It is a scalar quantity. Numerically, we just add all the paths traveled. For example, we take the example of a rectangle. Here, a body has to move from A through B and C to D. Then, the distance AD is equal to AB plus BC plus CD. Now, there are a few important points. When a body moves, magnitude of displacement can decrease or increase, while distance can only increase but never decrease. Point number 2. Distance is always positive. Now we need to see velocity. The rate of change of position of any particle in a particular direction is called velocity. Average velocity is defined as the ratio of change in displacement, that is del x, to time interval, that is del t, and that is equal to del x upon del t. Moving ahead, we have uniform velocity. The velocity of object is said to be uniform if it travels equal distance in equal interval of time. Variable velocity, the velocity of an object is said to be variable if it travels unequal displacement in equal interval of time, or vice versa. The velocity may be variable due to following reasons. First, change in magnitude, change in direction, and third is change in magnitude as well as direction. There is one important point that is to be noted. If the speed of an object is constant, its velocity may be variable due to change in its direction. Instantaneous velocity. The velocity at any particular instant of time or at a particular point of journey is called instantaneous velocity and is represented as dx upon dt. Uniform motion. If an object moves with uniform velocity along a straight line, then it is said to be uniform motion. In this case, v is always constant. Graphical representation of motion. Position time graph. If a body moves uniformly along a straight line with a speed v, the curve representing its position relative to an arbitrary origin versus time is called position time graph. For uniform motion, position time graph will be a straight line, as shown in the figure. Slope of a position time graph at any point gives the instantaneous velocity of a particle. We have two more graphs. On the left side, we have a graph means the graph is parallel to the time axis. It means the object is at rest, which shows that it is a graph of a stationary object. Moving towards right, we have another graph where the graph is traveling equal distance in equal interval of time. It means it is a graph of uniform motion. Moving ahead, we have another graph in which we will discuss three different parts. On x-axis we have time ta, tb and tc. On y-axis we have distance xa, xb and xc. Here, on the first part till ta, the body is peaking speed. In the middle part from ta to tb, the body is uniform velocity and the graph is a straight line. After tb, the body is slowing down the speed and it's coming to rest till tc, and after that the body is at rest. Now we will talk about velocity time graph. If the velocity is uniform, the velocity remains constant and the time goes on increasing. In other words, we can say that velocity time graph remains parallel to the time axis, as shown in figure. Here we need to note one more thing, that if we have a particular time interval, then we can find the area of the graph with time axis in that particular time interval, and then we can say that we have got the displacement. Moving on the next slide, we have the evaluation of the distance and displacement from velocity time graph. As velocity may be positive, negative or zero, its graph can be above or below the time axis. depicting positive velocity and negative velocity respectively. Total distance can be measured by adding total area because it doesn't have to do with the direction. While measuring the displacement, area above the time axis is taken as positive and below time axis is taken as negative. Note, the slope of velocity time graph at any point gives instantaneous acceleration. We need to discuss three more graphs. Position time graph for motion with positive, negative and zero acceleration. In the first graph of position time, we see that the graph is rising. It means that the distance is increasing with a less interval of time. It means it has a positive acceleration. Again, in the second graph, we have the distance is decreasing with a less interval of time. It means it is decelerating with negative acceleration. Now we have the graph of uniform motion. It means covering equal distance and equal interval of time. It means zero acceleration. On the next slide, we have the graphs of velocity, time, motion with constant acceleration for the following cases. First case is an object is moving in positive direction with a positive constant acceleration. On the y-axis we have velocity, on the x-axis we have time. It means that the velocity is increasing with time. It means constant acceleration, that is in the positive direction. An object is moving in positive direction in the second graph with a constant negative acceleration as seen because the velocity is decreasing with time. And in the third graph we have an object is moving in negative direction with a constant negative acceleration. Moving towards the next slide, we have rectilinear propagation of motion. One-dimensional motion of a particle in a given direction is known as rectilinear propagation of motion. Equations of motion. We need to understand these three equations, that is v is equal to u plus at, s is equal to ud plus half at square. Third is v square minus u square, that is equal to 2as, where v is the final velocity, u is the initial velocity, s is displacement, a is acceleration, t is the time. There are some assumptions for motion under gravity. First one is there is no air resistance, motion is vertical to Earth's surface, acceleration due to gravity is constant and is equal to 9.8 meter per second square. We need to consider some more points. In case of motion under gravity, velocity at maximum height should be equal to 0. When vertical moves upwards, it is retarded by g. So we put minus sign and it comes minus g. That is acceleration due to gravity in negative direction. Next, when particle comes down, its motion is accelerated by gravity and we use g for acceleration. So this is the end of the theory. On the next slide we will use some questions of HC Verma. Page number 52, question number 13, an important question. An object having a velocity of 4 meters per second is accelerated at a rate of 1.2 meters per second square for 5 seconds. Find the distance traveled during the period of acceleration. We will first write the data that is given in the question, and we have u is equal to 4 meters per second, a is equal to 1.2 meters per second square, t is equal to 5 seconds. We need to find s. Simply we will use the equation of motion ut plus half at square. Putting the value, we have 20 plus 15, that is equal to 35 meters. Moving towards the next question on page number 52, question number 15. A train starts from rest and moves with a constant acceleration of 2 meters per second square for half a minute. The brakes are then applied and the train comes to rest in 1 minute. We need to find total distance moved by the train, the maximum speed attained by the train, and the position of the train at half the speed. Here we have the data given in the question. U is equal to 0, a is equal to 2 into 2.0 meter per second square, t is equal to 0.5 minute, that is equal to 30 seconds. Part A, s is equal to ut plus half at square, that is equal to 0 plus half into 2 into 30 into 30, that is equal to 900 meter. We will stop here, and then we will find v, that is equal to u plus 80, means 0 plus 2 into 30, that is 60 meter per second. This final velocity becomes initial velocity for decelerated motion. Again, for decelerated motion, t is equal to 60 seconds, v is equal to 0, and u is equal to 60 meter per second square. That is calculated above. So using the equation, v is equal to u plus 80, or 0 is equal to 60 plus a into 60, or a is equal to minus 1 meter per second square. Using the equation, s is equal to ut plus half at square, and putting the value, we get 60 into 60 plus half into minus 1 into 60 into 60. That is equal to 1800. Therefore, the total distance, we will add the previous one and the now. That is 900 plus 1800, that is 2700 meters, that is equal to 2.7 kilometers. Moving ahead, we will need to find the part B, that is maximum speed is attained by the train is after half minute, and it's already calculated above, which is equal to 60 meter per second. Here part C, half of maximum speed during the accelerated motion is equal to 1 by 2 into 60, that is 30 meter per second. Now using the equation v square minus u square is equal to 2as, putting the values we get 900 minus 0, this is equal to 2 into s, or s is equal to 900 upon 4, that is equal to 225 meter. Again for decelerated motion, u is equal to 60 meter per second, v is equal to 30 meter per second, so acceleration is equal to minus 1 meter per second square. Using the equation v square minus u square is equal to 2as, we get 900 minus 6600, that is equal to minus 2 into minus 1 into s, or s is equal to minus 2700 upon minus 2, that is equal to 1350 meter. Therefore in this case distance will be 900 plus 1350, that is 2250 meter, that is 2.25 kilometers. Moving ahead, we have the next question on page number 52. Question number 23, a ball is projected vertically upward with a speed of 50 meter per second. Find the maximum height, the time to reach the maximum height, the speed at half the maximum height. Take g is equal to 10 meter per second square. For part A, at maximum height, v is equal to 0, u is equal to 50 meter per second, g is equal to minus 10, therefore v square minus u square is equal to 2as, or it can be written as 0 minus 2500 is equal to 2 into minus 10 into s. So we need to calculate s is equal to minus 2500 upon minus 20, that is equal to 125 meter. Now part B, we need to find time. V is equal to u plus 80, so b is 0, u is 50, a is minus 10 into t, so t is equal to 50 upon 10, that is equal to 5 seconds. For part C, v at half the maximum height, that is v dash. Using the equation v square minus u square is equal to as, or v dash square, that is equal to 2500 minus 20 into 25.2, that is 2500 minus 1250, that is equal to 1250. So v dash is equal to under root 1250, that is equal to 34.83 meter per second. Next question, page number 52, question number 24. A ball is dropped from a balloon going up at a speed of 7 meter per second. If the balloon was at a height of 60 at the time of dropping the ball, how long will the ball take in reaching the ground? Answer. As the ball comes out of the balloon, it will have the velocity of the balloon in upward direction at that instant. So for upward motion, u is equal to 7 meter per second for balloon and the ball, and v is 0, g is equal to minus 9.8 meter per second square. Using the equation v is equal to u plus 80, that is 0 minus 49 is equal to 2 into minus 9.8 into s is equal to 2.5 meter. Now the total height becomes 60 plus 2.5, that is 62.5 meters. From the equation s is equal to ut plus half at t square, we get 62.5 is equal to 0 plus half into 9.8 into t square. This gives t square is equal to 62.5 into 2 upon 9.8 is equal to 12.755, or t is equal to under root 12.775, that is 3.57. So total time is equal to 0.71 plus 3.57, that is equal to 4.28 seconds. Another question we have, page number 52, question number 26. A person sitting on the top of a tall building is dropping balls at regular interval of time, that is 1 second. Find the position of third, fourth and fifth ball when the sixth ball is being dropped. From the figure on the next page, position of all the balls are clear and the time interval of every ball is 1 second. Therefore from the top third ball, for third ball, t is equal to 3 seconds, u is equal to 0, we need to find s, and g is equal to 9.8 meter per second square. S is equal to ut plus half at square. S is equal to 0 plus half into 9.8 into 9, that is equal to 44.1 meter from the top. For the fourth ball from the top, t is equal to 2 seconds, u is equal to 0, z is equal to 9.8 meter per second square. We need to find s. Using the equation s is equal to ud plus half ad square. S is equal to 0 plus 1 by 2 into 9.8 into 4, that is equal to 9.6 meters. From the top, t is equal to 1 seconds, u is equal to 0, we need to find s. Again the same equation, s is equal to ud plus half ad square is equal to 0 plus half into 9.8 into 1, that is equal to 4.9 meter. So by going through these theories, we are able to solve these questions of HC Verma. It means these theories are okay and enough. So go through the questions, practice and do good. All the best.